Welcome everybody to example 1. In this example we're still looking at page 128 in the workbook, and this is going to be our very first example of an inner product. Okay, so for the first example we'll start with a familiar vector space Fn, and remember that just represents Rn or Cn. We're talking about tuples here. So we'll start with two vectors that are just n tuples in this vector space and define what's called the standard inner product. Okay, here's its definition. So the inner product of two vectors x and y is just going to be a big sum of products, basically. So we're going to take the inner product of x and y by taking the first component of x and multiplying by the complex conjugate of the second component. Then we're going to add that to the second component of x times the complex conjugate of the second component of y, and we're going to keep doing that and just get a big sum of products that look like that. Okay, so just so you get an idea for what that is saying, let's take a couple of specific vectors. So what if we were in R3, for example? What would this inner product be saying? Well, I'm just going to pick a couple of vectors kind of at random here. So let's say that we took 1, 0, -2 and took the inner product of that with 3, 1, -1 according to this definition. Okay, well, it's saying that we want to take the coordinates one at a time and multiply them together. And notice that since all real numbers are involved, we can kind of ignore the complex conjugate that's up here. Okay, if you take the complex conjugate of a real number, it stays the same. So really then, all we're doing with this product is we're taking the first coordinate in both of the vectors and multiplying them together, so we'll get 1 times 3. Then we'll take the second coordinates and multiply them together, that's 0 times 1. And then finally, we'll take the third coordinates and add them together. Okay, if you do the arithmetic there, you can check me out and notice that we're going to get 5 out of that. Okay, what did we really do there in that product? Do you recognize that process? This is really just the dot product of those two vectors that we calculated, the same product that you learn about in multivariable calculus. So I want to emphasize here that this standard inner product really is just the dot product. That's all we're talking about here. Okay, so what I'd like to do is see if we can take a minute or two here and prove that this dot product really does fit the definition of an inner product that we made up here. Does it really have those 4 properties? Okay, so let's take a minute just to write a proof of that. And this is a proof that the standard inner product is an inner product. Okay, and that statement sounds a little bit silly, doesn't it? It would be kind of a bad choice of terms to call it the standard inner product if it wasn't an inner product, but we want to confirm that it really is an inner product here. Okay, so to prove this, we just need to go down our list of properties one by one. We'll start with A and see if we can prove that this standard inner product has that first property. Okay, so, and actually, before we do that, okay, when we prove these 4 properties, we need some arbitrary vectors, so let's write that into our proof first here. So we'll let x equal x1 up to xn, y equal y1 up to yn, z equals z1 up to zn. Okay, there's our 3 arbitrary vectors that we want to talk about. Okay, well, let C be an arbitrary scalar. Now we're ready to confirm that we have those 4 properties, starting with A here. All right, so property A, okay, I'm going to scroll up a little bit. We need to look at the inner product of x plus z with y, and what we're hoping is that we can show that that has that sort of linearity property, that that's equal to the inner product of x and y plus the inner product of z and y. Okay, so first let's write out what this is. We kind of wrote down a general form for x, y, and z. We'll be going back and kind of referring back to that as we go through the proof. So x plus z would be what we get if we just add the two vectors x and z together. So that's going to look like x1 plus z1, x2 plus z2, and so on. Okay, and we're going to be taking the inner product of that with y, okay, which just looks like y1, y2 up to yn. Okay, so there's our starting point. And then we ask ourselves, what's the definition of this inner product? Well, that's sitting right here. Okay, basically just tells us that we need to add up a big product that consists of the components of our first vector times conjugates of components of our second vector. So by definition, this is going to look like the sum from 1 to n of xi plus zi times the conjugate of yi. We're just using the definition up here of the inner product of x with y. Okay, and then use kind of some of the standard properties of complex numbers, so we can take that yi and distribute it through and break this sum into two pieces so that it looks like this. Using properties of complex numbers, some of which we proved back in the last section. And then notice that what's kind of staring at us here, this first sum, is exactly the definition of the inner product of x and y. And similarly, the second sum is the definition of the inner product of z with y. And if you kind of notice where we started and where we stopped, we have just proven property A. Okay, so we are a fourth of the way there. Okay, and moving down our list, let's see. Property B, I'm just going to make the comment that proving that would be similar to the argument that we just did in A, so I'm going to let you kind of go back and try that on your own. And we'll move on and see if we can prove property C here. Okay, so property C, I want to scroll up and take a peek at it again. That was the one that said that the complex conjugate of an inner product of x and y just sort of flips the y and the x. It's the inner product of y with x. Let's see if we can prove that. Okay, so we'll start with the left-hand side. That's the complex conjugate of the inner product of x and y. So by definition, the inner product of x and y looks like a sum from 1 to n of xi, yi bar. Okay, and there's this complex conjugate over the top of it, so it would look like that. Okay, and I'm going to remind you that it's possible to take complex conjugates and split them up, so we could rewrite this as the sum from 1 to n of the complex conjugate of the inside part. What did we use there? Well, basically the fact that if you take the complex conjugate of a sum of complex numbers, you can just take the conjugates of those numbers one at a time and add them up. We actually proved that property for n equals 2, and you could generalize it using a proof by induction. Okay, so we're sitting here now, and taking that one more step, we actually proved also that the complex conjugate of a product of two numbers is the product of their conjugates, which means we could rewrite this like this. Now this is kind of weird. If you look over here at the yi term, we've got the complex conjugate twice, and if you think about that for a minute, if you conjugate a number twice, you're just going to get back to the number itself. Okay, I'm going to let you check that on your own. Okay, so we're sitting here, and I'm going to note that we could write those numbers in the opposite order. xi bar times yi is yi times xi bar. Why is that? Well, because complex multiplication is commutative. We can switch the order of multiplication. We're just talking about scalars here. And you might notice that this very last line the sum from 1 to n of yi times xi bar, that's the very definition of the inner product of y with x. Okay, and so looking at where we started and looking at where we stopped, that is property C. We've just proven that that's true. Okay, and we've got just one to go here. Okay, so if we just sneak a peek again, property D is the one that says we want to see if we can show that the inner product of a vector with itself is always positive provided that x is not 0. Okay, let's see if we can do that. So we need to start with a non-zero vector. Okay, and up until now, when we've written the 0 vector, we've denoted it kind of like that, a 0 with a bar over it. I'd like to avoid that notation now because in this chapter, that bar generally means complex conjugation. So avoid confusion, I'm going to change our notation for the 0 vector a little bit. From here on out, I'm going to try to write that as 0 with a v. That means the 0 vector in the vector space V. That's a way of being able to look at that and notice that it's a vector and not a scalar. Okay, so let's just make a note to ourselves that that notation just means the 0 vector. Okay, and then we ask ourselves, well, what does it mean for a tuple to not be the 0 vector? Well, it just means that at least one of the coordinates in our tuple has to be a non-zero scalar. So let's start by making that observation. So xj, one of its components is not equal to 0 for some j. There's our setup. And now let's see if we can show that the inner product of x with itself is positive. Okay, so starting with inner product of x with x. By definition, that's the sum from 1 to n of xi bar. Okay, that just goes back to how we define the standard inner product. Okay, and then we come to a property that we proved in section 6.0, the fact that the product of a complex number with its conjugate is the modulus of that complex number squared. Okay, so we can rewrite this as that. And notice that that is a real number that we're looking at. Okay, and here's where we remember that we made the observation above that one of the coordinates is not equal to 0, so that means when we look at this sum, there's got to be at least one term in that sum that's positive, which means that that sum is going to turn out to be positive. Okay, remind ourselves where that came from, because xj was greater than 0. And that's exactly what we wanted to prove. So we started with the inner product of x with itself, and we got something that's positive. Okay, so we have just verified that the dot product satisfies the 4 conditions in our definition of the inner product, and in future examples we'll take a look at other inner products defined on more abstract vector spaces.